We're going to continue our study of circuits by looking now at circuits that contain both capacitors and inductors along with resistance. These types of circuits are referred to as second order and sometimes higher ordered circuits. My name is Lee Brinton. I'm an electrical engineering instructor at Salt Lake Community College. As we study these types of second order circuits, we'll look at both the natural response and the step response, looking specifically at parallel and series connections of resistors, inductors, and capacitors. We'll start our discussion of RLC circuits by studying the natural response. The natural response of a circuit refers to the way energy stored in a circuit dissipates when the source of the energy is removed. Earlier in this class, we discussed the natural and step response of circuits with resistance and either inductors or capacitors, but not both. These circuits led to a first-order differential equation that we then solved, and the solution to that differential equation was of the form, the natural response was of the form x of t, where x was either a voltage or current in the circuit, was equal to some initial quantity times e to the minus t over tau, where for circuits involving resistors and capacitors, tau equaled r times c, and for circuits involving resistors and inductors, tau equaled L over R. Now we combine or place into the same circuit both capacitance and inductance. We're going to see that the energy stored in inductors and capacitors, of course energy stored in the inductor in the form of a current flowing through the inductor or a voltage across the capacitor, we're going to see that as the source of the energy is removed, there can be interaction between those devices that leads to a more complex response than a simple exponential decay. We're going to see that this type of a circuit is described with a second-order differential equation. Okay, let's go ahead and start our analysis by determining the natural response of the parallel RLC circuit. We're going to assume some initial voltage on the capacitor as being V0, and we'll assume that there's some initial current in the inductor at 0, and let's be explicit, 0 plus, the moment after the switching event. We'll call that I0. Because they're in parallel, the voltage across the capacitor is also the voltage across the resistor and that across the inductor. And of course the current through the inductor will just define like that. So plus to minus voltage there and current flowing through the inductor that way. So there's some initial quantity, V0 and I0 at t equals 0, then the energy in those devices is allowed to dissipate. And the purpose of our analysis is to describe the way that that energy dissipates by solving for either the voltage across the parallel or the current through the inductor. To do this, we're going to start by writing a node equation summing the currents leaving the node. Let's define I sub r down that way, I sub c like that. We've already got I sub l. All three of the currents are defined leaving the node. So we have then I sub r plus I sub c plus I sub l. The sum of those three currents has to equal 0. Now, I sub r is just the voltage across that parallel system divided by the resistance, plus the current through the capacitor, which is just C times the derivative of the voltage. And then the inductance as or the current through the inductor as a function of the voltage is equal to 1 over L times the integral from 0 to t V of, call it x dx, plus some initial current. And the sum of those terms then must equal 0. This type of equation is known as an integral differential equation. It has both integration and, or integrals and derivatives present. Given that this is a homogeneous equation where the source, where there is no source, and so the right-hand side of the equation is 0, we can differentiate both sides of the equation one time with respect to t to eliminate the integral. We're going to, as we do that, we'll rewrite this in terms of highest order differential term and then decreasing, or in decreasing order of differential terms. So differentiating both of these both sides of the equation here, taking this term, we have C times the second derivative of the voltage with respect to time, plus 1 over R times the first derivative of the voltage with respect to time. That's the derivative of this term here. Now the derivative of the integral, of course, just eliminates the integral, and we're left with plus 1 over L V. Now the derivative of a constant is 0, is equal to then 0. Now if we divide both sides of the equation by C, we get then, in its standard form, the second derivative with respect to time of the voltage plus 1 over R times C times the first derivative plus 1 over LC times V equals 0. In this form, we recognize this as a second-order differential equation with constant coefficients. It's linear, and it's also homogeneous. In a course in differential equations, we learned that this type of a problem, or this type of a differential equation, can be solved by inspection. It's an interesting problem here. We have the variable v, that's what we're looking to solve for, plus its first derivative, plus its second derivative, all must add to equal 0. What that tells us is that in order for these to all these terms to cancel, it tells us that the variable v, its first derivative, and its second derivative must all be of the same form. Now you'll recall from your differential equations class, two families of functions meet that general criteria. The trigonometric functions sines and cosines and their derivatives are of the same form, and also the exponential functions. It turns out that the exponential function satisfies this equation, and we're going to simply write or assume the form of the solution v of t is going to be of the form a e to the st. Now, in order to come up or to solve this, we're going to need the derivative with respect to t, which is a s e to the st, and the second derivative with respect to t then will be a squared, no, a s squared e to the st. Now with these expressions of v and the first and second derivatives, we can plug those into our differential equation, and we get the second derivative a s squared e to the st plus 1 over rc times the first derivative a s e to the st plus 1 over lc times the variable itself a e to the st equals 0. Now you'll notice that each of these terms have an a e to the st term in common. Let's factor that out. A e to the st then, which leaves s squared plus 1 over rc s plus 1 over lc equals 0. Here we have two terms multiplied together that must equal 0. Either the first term a e to the st or the second term within the parentheses must equal 0. The only time a e to the st equals 0 is the very non-interesting case where a equals 0, and we'd be simply plugging in, saying that v is 0 and v and the 0 plus the derivative 0. But that's not a terribly interesting or meaningful solution. The other solution then comes when this quadratic term is equal to 0. Taking that and setting it equal to 0, we have what is known as the characteristic equation for this circuit. And throughout the rest of this course, we're going to find that this expression pops up all over the place, that it is in fact an equation that characterizes the parallel combination of R, L, and C. Now, we want to determine what values of S will lead to the solution for this differential equation here. To do that, we'll use the quadratic formula. It says then that S is equal to negative b, which is negative 1 over RC, plus or minus the square root of b squared, 1 over RC, squared minus 4 times a, which is 1, times c, which is 1 over LC, all divided by 2 times a, but again a is just 1. Now let's bring this 2 in the denominator up into the denominators of the numerator terms. So we'll have negative 1 over 2RC. This then is equal to negative 1 over 2RC plus or minus the square root of. Now, this 2 outside of the radical comes into the radical as a 4. Now I've got, at this point right here, I have this 1 over RC squared. So inside the radical it's a 4. If I bring it inside the parentheses here, I'll bring it in as a 2, because the 2 then would be squared. In other words, I end up with 1 over 2RC quantity squared minus, now once again, this 2 into the numerator. Into the radical comes in as a 4. It's in the denominator, so it's going to cancel that 4. And we're left with simply 1 over LC. Because of the plus and minus terms of the quadratic equation, we have then 2 values of S. We'll call it S1 and S2. And to accommodate those 2 values of S, we're then going to expand to a complete solution. V of t then is going to equal some A1 e to the S1t plus A2 e to the S2t, where A1 and A2 are constants that are dependent upon the initial conditions of the circuit. And we'll use the initial conditions to determine A1 and A2 as we go forward. But first, we need to look at these terms now. A1 and A2, as we've already pointed out, are constants dependent upon the initial conditions. S1 and S2 are known as complex frequencies. Dimensional analysis of the exponent here, we have seconds, t is in seconds. In order for the exponent to be dimensionless, S must have the units of 1 over seconds, or per second, which is a frequency term. So S is known as the complex frequency. We're going to define 2 other terms. First, the term alpha. Alpha is equal to 1 over 2RC. It's known as the neper frequency. We're going to see that because it has the same units as S, it is also a frequency in reciprocal seconds or per second, and again, it is then a frequency of sorts. We're now going to define one final term. We're going to call it omega naught, which is equal to the square root of 1 over LC. This is known as the natural frequency or the resonant frequency of this circuit. When we do these, when we make these substitutions, then this expression here for S1 and S2 becomes a little more simplified. Or we have then that S1 and S2 is equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared. As you look then at that term, let's rewrite it. S1 and S2 are equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared, where alpha squared is equal to 1 over 2RC, and, alpha, not alpha squared, but alpha is equal to 1 over 2RC, and omega naught is equal to the square root of 1 over LC, or omega naught squared then is equal to 1 over LC. Notice that we have alpha squared minus omega naught squared, and that alpha is dependent upon the values of the resistance and the capacitance, and the natural frequency omega naught squared is proportional, or is dependent upon the inductor size and the capacitor size. So depending upon the values of R, L, and C, alpha may either be bigger than omega naught, alpha may be less than omega naught, or alpha may be exactly equal to omega naught. We have three different cases dependent upon the value of the discriminant. Let's look first at the situation where alpha squared is greater than omega naught squared. Under these circumstances, then, this term here under the radical, the discriminant, alpha squared minus omega naught squared will be greater than 0. It'll be a positive number. In this case, we will have S1 and S2 being distinct. S1 and S2 are distinct, real. Let's emphasize the fact that they are real values. Now, for the case when alpha squared is less than omega naught squared, the discriminant here, the value under the radical, will be negative. Alpha squared minus omega naught squared will be less than 0 or negative. And S1 and S2 are complex conjugates of each other. We still get two distinct roots, but the roots are complex and they are related to each other as conjugates of each other. Finally, we have the situation where alpha squared is exactly equal to omega naught squared, so that alpha squared minus omega naught squared equals 0. And under these circumstances, S1 and S2 are the same value. They're negative alpha. S1 and S2, a repeated root. And the math people like to say that it is a multiplicity of 2. We thus see that the nature of S can take on any one of three different forms based upon the relative values of R, L, and C. We're going to see that the following terms for these will make a lot of sense. But for right now, we're going to simply refer to the case where the roots are real and distinct. We're going to say that that is an overdamped, D-A-M-P-E-D, overdamped circuit. When alpha is less than omega naught, we're going to say that that is underdamped. And when alpha equals omega, we're going to say that that is critically, C-R-I-T-I-C-A-L-L, critically damped. In the next few videos, we're going to look at the response, the natural response of this parallel RLC circuit for the case where it is overdamped, underdamped, and then critically damped. We're going to see that the shape or the form of the solutions to these differential equations are uniquely different, are unique. They're different from each other depending upon the circuit's dampening.